I think it's because that's the way the brain really works well, right? So here we're going to have, you got a mammal and you got dog and you got German Shepherd, right? And there's this idea that the German Shepherd is a mammal, right? And right, and so mammals will have certain properties, like they nurse their young, and so then we know that all types of dogs do that, right? Because they're all mammals. And then, right, we say the child class extends the parent class. Right? Everybody, you all know this already? All right, so we'll go fast, and maybe you'll know the whole course, and life will be good. Right? Right, and so you're inheriting, right? The German Shepherd is inheriting from the mammal the fact that it nurses its young, right? So it inherits data, and it inherits methods, and we can add new data and new methods, and you can overwrite, the German Shepherd might overwrite the general way of doing something, and then the Labrador might do it slightly different. But the big concept is the same. And so that's kind of interesting. Somebody on the outside might say, oh, well, I need my guy to walk. And now mammal has a concept of walking, but, dogs might walk different than horses and stuff, right? So the underlying can be the same. And so here how we have, and then there's these things called interfaces, where it kind of tells you what the routines are, what the basic data structures are, but without giving you any actual code, right? And so here could be one which is a collection, and then a set is a collection, and a list is a collection, and so there can be some, but it's only down here where you actually put in code. Right? People know this already too? All right? Holler when you don't know something, right? Finds concepts. That's why, I thought we would know this already. Science abstract, right? So the interface defines what the inputs and outputs will be. Maybe it'll even give some abstract meaning that what these things are supposed to be without actually implementing it, right? Now, you could have somebody inheriting from more than one, like this guy here is both a pet and it's a robot, right? A cat is both a feline and it's a pet. But evidently in Java, you can inherit lots of interfaces, but only one class, only one code. I don't know why. Does anybody know why? I don't know why. Right? But in C, evidently you can have lots of, you can inherit from lots. Right, so here's just the code. So I guess we're doing a little code there, right? We say it's a class and it's a subclass. All right, this subclass extends this bigger class, and it implements these interfaces, and it overrides, right? And it implements some of the interfaces that don't have code. You have to implement them, and it overrides some of the codes from the superclass, and it defines some more things. This is a quote I like from Donald Knuth. Donald Knuth wrote Emacs and LaTeX and various things. Anyway, he says to be a good programmer, but I think really to be a good anybody is you have to be able to move between the layers of abstraction and kind of focus on the right layer, right? Worry about things at the right level. This might be completely, I don't know. We'll see. Let me know whether this is all stuff you know or not, but it's going to be quick, so it won't kill you too badly. I had to give a general talk to mathematicians about computer science when I was in Africa, and I made up these slides, and then I stuck them in here. All right, so it's all about hierarchies. So what's the hierarchy? Actually, then I started at the bottom that we started with sand, and we worked our way up to building circuits. But here it's a Reader's Digest of that talk. Right at the bottom, we can build semiconductors. On top of that, we can build transistors. Right on top of that, we build AND gates. Right, and on top of that, you build little simple circuits. Right, you can see at each level, you want to worry about what its problems are. Right, relying. This is where it comes to about trust. I was talking about trust. You want to trust that the layers below you are working, and to build up the next layer. Right, you can't worry about it all at the same time. Right, so you build simple. That one on the right is a simple memory. Right, and then you build banks of memory, and then you build hardware, right? And then you get an operating system that can load and code, right? And low-level coding, which is machine coding. My first job was writing a program to compact images, and I wrote it in machine code. So that was a term. And then you get higher level coding, like finding shortest path and loops. Oh no, we're not quite there yet. This is just for loops. And then we have object-oriented things like stacks and pops, and right, we have objects, and then we have algorithms where now we can find the shortest path between two nodes in a graph, right? And we can move up to all the various things you could study in grad school. All right, everybody kind of got the hierarchy? You've probably seen it. You probably knew it all before, but. Oh, good question. I think we'll be somewhat moving between them. So 3101 is definitely here. I think we're going to be a little bit more down here, right? I mean, this course is on more of the data structure, so somewhere between these two. Right, so the key at a level is not worrying about trusting the levels below you, right, and having contracts with the lower level below, right? I'm going to start, when I build my little circuit, I'm going to start with leaving that you've given me a bunch of AND gates that are going to work. I'm not worrying about the silicon, right? All right, so I used to have a slide that said 3 people, and then I read over the slide a couple days ago, and I turned it into 5 people. So let's see who our new people are. Right? We have the boss, and we have the mathematician. Those are actually the 2 new people. And then we have the implementer and the user, and then the end user. All right? So again, when we're talking about who are you, you want to think, well, I'm going to wear this hat for a while. Now I'm wearing this hat for a while. Right? So the boss has to design, what it is that we're trying to do, right? The specifications of the programmer. The mathematician needs to design the algorithms. The coder is implementing the data structure here. And then the user of the data structure, right, is going to write code using that data structure, right? And then the end programmer uses it all, right? He has a cell phone, right? And right, so what's everybody's goals, right? His goal is to make the end user happy and to make money. The designer's goal, the mathematician's goal is to prove that all the codes are correct and are efficient, right? The implementer, I copied from the slide before that, which I copied from James Alder, of course, is you want your code to be readable and understandable, and you want it to be, here before it said we want it to be correct, right? Well, it sort of separated these 2 jobs. This guy is making sure the algorithm is correct, right? And this guy is making sure that the code is implementing the algorithm, right? So even as you're doing your projects, you want to first be the mathematician and come up with a good algorithm, and then make sure you implement it correctly, right? So it needs to be robust and adaptable and portable, like we were talking about, right? Right, and now this guy, he doesn't know anything about how it's implemented, right? He just knows the the contract that's coming to him. And he plays with this stuff. This guy here, he's using his data structures, right? So here we're going to be, who are we? We're over here. We're doing data structures. So we're going to talk about what are the algorithms for a balanced binary tree, and how do you implement it, right? And then this guy, all he does is he uses the data structure, and he doesn't know how he doesn't need to know how he knows it's a dictionary, it's a stack, right? Right? We're good?